Good morning, my dear students. Today we are going to continue the robotic control system, it's a part 2. So last class you have been discussed about a mathematical model of a link joint. Why I represented it as a mass and a damper and the friction coefficient. Also we already discussed about the dampness. Okay, so what happened when the poles are real and distinct, when the poles are complex, when the poles are real and equal. So we have been discussed different conditions. Okay, so today we are going to continue how those type of second order system can be controlled using different controllers. Okay, you normally knows very well about on-off controller, proportional controller, integral proportional derivative, and proportional integral plus derivative, PID, etc. Okay, but you know how those laws, the control laws, are generated, or why we normally fix some control law. Okay, the PID, PD, PI, these controls are called control laws. So the control laws have some constants. We have to generate those constants using or setting the control laws, right? So we again we have been assumed that the sensors which are capable of detecting the blocks, okay, the control system blocks of a position and the velocity, whose position and the velocity. So there will be a position sensor encoder and a velocity sensor, speed tacho generator or tachometers, right? Now in this class we are going to propose a control law and computes the force, compute the force which should be applied by the actuator as a function of the sensed feedback. Okay, so why we again dealing with this second order control system means, say again I used to write the control of second order control system. Second order control system. Okay, so again we go back to the diagram. So this is the typical representation of mass and the stiffness coefficient, the displacement x, the force is the input, force F is the input. So this system, this block, this mechanical system is represented by a second order equation. You know that whose equation is F equal to mx double dot m d square x by dt square plus b x dot b dx by dt plus k into x. Okay, this you know. So now we are going to propose a control law, okay, which computes the force, okay. So force which should be applied, this force should be applied by the actuator. What is actuator? Actually, the actuator is a joint link. So what is in the joint? In every joint there is a I will show that diagram. See, at every joint, this is the motor or drive torque. So the drive torque, this is the drive torque, drive inertia. This is the ratio between the links and the gear system, eta, and the mechanical torque. So you see here, this portion, this is the link inertia. The link is connected to the electrical motor, okay, actuator. That is called actuator. So between these two, there is a stiffness. So that stiffness is a flexible joint. So flexible joint motion. Okay. Similarly, the joint damper. So this is actually I represented as B. So joint damper. This is a K, J, moment of inertia. Okay. See, this is the typical representation of a joint. So this the transfer function is of second order. Okay. So same, this can be written as tau equal to J x double dot plus B x dot, theta double dot plus k theta. So this is for angular displacement. This is for linear. Okay, this is for linear motion. This is for angular motion, angular joint, angular movement, right? So what we are going to propose it, we are going to generate a control law. So the control law, what is the feedback to the control law? That is the sensors. Okay, the sensed feedback. So sensed feedback. What is sensed feedback? That is F equal to minus Kp times x minus K V times x dot. So proportional times the displacement minus velocity. This is a position feedback. Position feedback. This is velocity using the velocity sensor. Velocity feedback. Velocity feedback. So this for this damper and mechanism, you see, this is the link. So that's why I am starting from the basics of second order mechanical system with the various poles and zeros. Understand? So, so I am going to develop using these relations. I am going to develop a control system. Okay, control system. What is how do we develop a control system? Please listen carefully. If you do not listen, you cannot understand the concept, right? So this is the robo system, robo or a system. Okay, simply robo or system. Here in our case, we consider the mechanical this system. Okay, so this is the system. The system is represented by a second order transfer function. Clear? So this system, from the system, there are two feedbacks. Okay, there are two feedbacks. One is kV, velocity. This is x dot, velocity feedback. This is the position feedback. So position Kp. Position feedback. Clear? So both are negative feedback. So minus kV minus Kp. So what is the output? The feedback force, right? So F. What is F? This is X. Please listen. F. What is F? F equal to, sorry, X minus X times Kp minus X dot times Kv. That is equal to K. So this closed loop diagram, where the left part, say you can say this part, I will show you. So that the dotted line, okay, this block, the dotted line covered by this block, okay. So in this, the dashed line, the closed loop dashed line, inside the dashed line is the control system, okay, usually implemented in the computer, okay. So if you want to implement a digital controller, this should be these constants and the parameters implemented in the computer, okay. So this is computer algorithm. So this is the control, either it can be called as a controller or control algorithm. Say PID control algorithm. What is PID control algorithm? Kp times E, Kb times ed by dt plus K times integral of di by dt. So we are adding normal position, then velocity, then integral, right? So this is normally implemented in the computer, okay, in the computer. So on the right side is a real plant, real system, okay. The system is a physical system. In this figure, there is an interface between the system and this is the computer. So here the control law, this is linked with the robot, okay, robot. There is an interface between computer controller and output actuator commands. So what is here? Actuator commands, and the input sensor information. So input to the computer is sensor information, output from the controller is actuator command. So that command passes to the robo arm. So to move, which direction, which displacement, which velocity, and so on. Okay. So this is a typical representation of a single link robo joint, which acts as a second order system. We are following only the linear. We are considering the single joint as a linear system, right? It is a linear system. Clear? So next, the control system we have proposed is a position regulation system. So what we proposed is a position regulation system. Position, I already told you. That the controllers, whatever we generated to regulate the set point, whatever controller we developed is to regulate the set point. Whereas the discrete controllers, the PLCs, only not regulating about the set point. Those controllers are discrete in nature. Okay, they are designed to maintain the different set points, different levels. They are not used to regulate. So in this robo control system, we have proposed is a regulation system. It simply attempts to maintain the position of the system, robo, okay, position of the robo in one fixed place, okay. So it maintain position at one fixed place, regardless, okay, regardless of disturbances. We are not considering disturbances here. Regardless disturbances, forces, okay, disturbance forces applied applied on the system or robot, on the robot. Okay, so here we are doing position regulation system. Okay, so in there is another also that control system called trajectory planning. Okay, trajectory following. One more control system we are going to discuss in the forthcoming lecture is trajectory planning. Trajectory following control system. Following control system. Okay, which can never cause the block, okay, to follow the desired position trajectory. So this is for this thing. So as we see in here, we are going to generate a control law between the system, and the feedback. Okay, and the system and the feedback. So how you see m mass into x double dot plus b x dot plus k x, which is equal to f. We also from the diagram, what is f? This f. What is this f? This f is in the system, input is f. Okay, force. Same force is applied to the input. According to this control system block, please understand. According to the control system block, this f, what is f? From the feedback, the f is minus kp times x minus kv times x dot. So same thing can be equivalent here, minus kp times x minus kv times x dot. Okay, understand or not? So you combined the left and the right side of this system, both are equal only. So now I am going to modify m x double dot plus taking b plus the x dot coefficient b plus kv, x dot coefficient. Okay, so from minus to plus k plus kp times x equal to 0. Now we generated a control law, right? Now you know in the second order steady state error response, kp is position constant, kv is a velocity constant. If you go in terms of PID controller, kp is proportional gain, kv is derivative gain. Okay, derivative, because kv is derivative of the displacement, so derivative gain. Clear? So now I am going to modify this expression as b dash and this expression as a k dash. Okay, let's see. So m, now the entire relation becomes m x double dot plus b dash x dot plus k dash x equal to 0, where b dash is b plus kv, where k dash is k plus kp. Understand? So it is clear that the choosing our control system. So that it is clear from this, choosing of the control gains, choosing of control gain. What are the control gain here? B dash and k dash. Okay, or b kv and kp. Okay, control gains kp and kv. Okay, we can cause a closed loop system to appear to have any, okay, to have any second order behavior that we wish. Okay, using this controller gain, we can control any second order system. Okay, so often these gains would have been would be chosen. Okay, would be chosen to obtain the critical damping. Normally, critically damping. So, what is the condition for critical damping for this mechanical system? For this mechanical system, tell me, anyone, what is the critical gain condition for the mechanical system when critical damping is zeta equal to 1? So, when zeta equal to 1 for at this condition, what is your B dash? Can you tell me what is your B dash? My dears, anyone please tell me? Very simple. From this second order system, we obtain omega n and zeta expressions, and on compare with s square m plus bs plus k equal to 0. So from this expression, we found zeta and b value. So when zeta is 1, what is the b value? B dash 2 times root of mk dash. Okay, please remember. Jayashree, okay, and some desired closed loop stiffness. We also, this is the gain, controller gain chosen, the controller gain would be chosen for critical damping. Critical damping. Jayashree is not feeling well. Good. Consider the answer. Okay.
Sorry, sir.
So similarly, the desired some desired closed loop stiffness. So this is a closed loop, actually controller closed loop gain would be chosen for critical damping. Similarly, closed loop stiffness K dash can be chosen for critically damping as, what is that critical damping? If you are சொல்லுங்க. Any idea?
So b dash by 2 the whole square.
Yes. சொல்லுங்க.
b dash by 2 the whole square by.
I am asking K value. Sorry. What is K value? Okay. From this also you can test. Okay. So B dash by 2. What you are saying? B dash. No, square.
By 2 the whole square.
B dash by
2 the whole square.
Right. B dash by 4. 4m, right?
So b dash square by 4, sir.
B dash square by for M. Sir, good.
So
Good. Note that the Kp and Kv, note that Kp and Kv may be positive or negative. May be positive or negative depending on the parameters of the original system. So the Kp and Kv are depending on the parameters of the original system, maybe positive or negative, it depending on maybe positive or negative depending on the parameters of the system, parameters of the robot. Okay, parameters of the original system. Here robot, okay, single joint robot. However, okay, however, if B dash and K dash become negative, okay, negative. Let us see one simple example. The parameters, for example, okay, simple example. Take M equal to 1, mass of the system, robo 1, B is 1, K is 1. We already discussed this problem in the previous class. Okay, find Kp, please do it. Find Kp and Kv for position regulator, for position regulation control law. We have to find the Kp value and K value for the position control law, which results in the critically damping. Okay, which results in the critically damping theta equal to 1 for the closed loop stiffness. What is closed loop stiffness? Closed loop stiffness is equal to 16. Okay, closed loop stiffness is 16. That is K dash. So what is the solution? Tell me, what will be the solution? What is the solution? We know B dash for critically damping is 2 root M K dash. So K dash is given. So we can find B dash. What is B dash? B dash equal to 2 root M is 1, K dash is 16. Closed loop stiffness 16. So 4. So B dash is how much? B dash is 4. So 2 into root of 16. So B dash is.
Sir, B dash is 8, sir.
Sorry,
8, sir.
Very good. B dash is, so root 16 is 4, 4 into 2, 8. Very good. So this is 8. So since, actually, if we see, since K equal to 1 and B equal to 1, we need, okay, what is the closed loop Kp value? What is Kp value? Please tell me. What is Kp and Kv? See, here what is Kp and Kv? K dash and B dash is known. So Bk is known. What is Kp and Kv? So we know that B dash equal to B plus Kv. We know K dash equal to K plus KP. Substitute here 1 plus KV is unknown, B dash is 8. So what is KV? 8 minus 1, 7. Okay. So KV is 7. Similarly, this is 1 plus KP. What is KP? KP is to be found. So what is K dash? K dash is 16. So 16 equal to 1 plus KP. What is KP? 15. So this is the method of finding the controller gains for closed loop system. Okay, so that's why I am telling you, even KP and KV are positive or negative, that depends on system parameters, right? Now, next is control law partitioning. Okay? Partitioning. So control law partitioning. Okay. Okay, so in this method, the we will position the we will divide the controller into model-based problem and servo-based problem. Okay, so the controller controller partitioning. Why it is partitioning means the entire controller, the position controller is separated into two parts, two positions or partitions. So that what are the two partitions? One partition is called model-based portion. Another one is servo. Okay, and another one is servo. Servo is feedback. Servo position or servo portion. So the position controller can be partitioned into two systems. One is position model based, another is servo based. Okay. So the system parameters for this case, the system parameters M, B, K. These are all comes under model based. Okay. So the KP, KV feedback terms. Okay. Those parameters are called servo portion. So in this case, we can have see in this case model. What is model? Model based portion. The entire feedback here. See, let us see here. So entire system we can divide it into servo. The underlined portion is servo portion. The system model. So this model is model. What is modeling equation? M d square x by dt square plus again this equation. So this is, if you use this equation, this is model based portion. Okay, servo based portion. So this is appears only in the model based portion. The servo portion is independent of these parameters. Actually, this servo model portion depend on, in this case, M, B, K. So the model portion mainly involved with M, B, K. This is the system parameters. Okay, system parameters. Whereas servo portion is totally independent of these parameters, system parameters. So servo portion independent of these system parameters. At the moment, this distinction may not seem important, but it will become more important as we consider non-linear system case. So in this system, it's not it's not seen very difficult or important. Suppose while I am starting from this point is we are moving towards non-linear control system. So this is a linear control system. So we are simply avoiding the disturbances, everything, noise, everything. We assume the initial conditions. When we move towards the non-linear controller, this become more important as we right for the linear control system. Okay, so we will adapt control law partitioning for the non-linear. Okay, control law partitioning for the non-linear is more important. That's why we start from this portion. Okay, the open loop equation of the motor. Okay, the open loop, we know the model, the open loop equation of motion for the system mx dot plus bx dot plus kx equal to f. Okay, so the model based portion of the control appears in a control law. We are going to now only we are going to develop the control law whose form, okay, the control law form equal to f equal to alpha times f dash plus beta. So now we are introducing a control law portioning, okay, which is nothing but the model based portion of the control appears in a control of the form that we are generating. Okay, I will justify why we selected this. So f equal to alpha times f dash plus beta. So what is from when comparing with this relation, what is f dash, what is alpha? F equal to f dash. What is alpha? Can you tell me what is f dash? So f is force, right? F is force. F dash is, what is the reduction of the force? F equal to, understand or not? F equal to say m d square x by dt square. So if you differentiate this f dash, it becomes when compare with f dash, what you will get? Anybody? The alpha and beta are the functions or constant of a law. Okay, law. The new input to the system. Now we consider a new input to the system. The new input to the system. The system appears to be unit mass. The system appears to be unit mass. Okay, what is unit mass? Unit mass is nothing but your x double dot. X double dot is nothing but your m is unit mass is nothing but a constant that is considered as a alpha, right? So alpha equal to, that's why we can write alpha equal to m because of its unit mass. Now you go back to this equation when alpha equal to m. Okay, so when alpha equal to m, so alpha times m. Okay, so this becomes what? So when compared with this relation m double dot, okay, so this portion is partitioning. So unit mass, this is alpha, this is beta. So this is beta. So what is x double dot? F dash. F double dot is f dash. Clear or not? So alpha equal to m, beta equal to b x dot plus k x. Clear or not? So what is x double dot? X double dot is equal to f. Clear? F double dot is equal to, sorry, f dash. F dash. F double dot equal to f dash. So now we are partitioning the control system with by also we are introducing a new control constants, control parameters alpha and beta. Now let us modify the previous system. What is the previous controller block diagram? You please go through that. So the previous control block, this is the previous control block. Now we are going to partition this control block by introducing new control constants. Those constants are called alpha and beta. So by considering the unit mass of the system m, so that is m equal to alpha, then beta equal to the remaining parameters b x dot, then k plus k x. Okay, now you see the unit mass is separated. Okay, we are modifying the block. Robo, that is system, any system. Okay, so far we are considering the only one link, one joint. Okay, so if you increase the joint, the system becomes more difficult, more non-linearity, right? Non-linearity also increases. Clear? So from the system, there are two parameters coming out: x, position x, and sorry, this say position. This is x dot velocity. Clear? So now plus. Okay, so the direction is very important. Then here this is kV. So kV comes from the okay. So this is minus, this is also minus somewhere. So this is f dash. Okay, plus minus plus. Then the what is the input to the system? F. So f is the input to the system. So f dash is here. So what is f actually? So what is here? This is nothing but bx dash plus kx. So bx dash plus kx. So from the x dash, it is fit to here. So sorry, I made one mistake. This is 2x. So this is directly goes to this. Understand? So this is x, this is x dash. Okay, x dash. So this is x dash, this is x. Right. Right. So f equal to, from this side, f dash. What is f dash? F dash is kp times x plus kv times x dash. Okay, x dot. What is f? F dash m plus b x dash plus c. See here, So what is F from this block? So F equal to what is available here? F dash M. So we consider alpha. This F dash is M is a alpha. Okay. So F dash M plus Vx dot plus Kx. So what we consider? This is alpha, this is beta. So this is beta, this M is alpha. Clear? So the closed loop system employing the partitioning method. Okay, what is the partitioning method again? This portion. See, we are partitioning here by developing a controller. So this is partitioning. So the left and the partitioning method. So this equation of motion for unit mass, right? Now we propose a controller. Now we propose a controller. We can proceed as the open loop dynamics of the system to be controlled. The open loop, okay, open loop system dynamics are controlled. So design a controller to compute. Let us design a controller. Okay, to compute, because the left portion is the partitioned portion is in the computer, right? The partition portion is in the computer. This is in the computer, okay, our controller. So let us design a controller to compute F dash. F dash is the output signal from the controller to actuate the system. Okay. So what is F dash? How to compute this? You just you follow the previous one. Okay. What is previous one? F equal to what is the previous one? F dash F equal to minus Kp times X minus Kv times X dash. So this we consider for this control block. So for this control block, we consider this equation, right? So for the new partitioning method, similar to that, F dash, okay? So F dash, same control law can be applied here. F dash equal to minus Kp times X minus Kv times X dash. So the combining this control law with this existing yields, okay, by combining this controller, combining this control law with the equation. Okay, with the equation, what is the equation? M double dash, like that, right? So what do we get? X dash X double dash plus Kv times X dash plus Kp times X equal to 0. Using this methodology, the setting the control gains is very simple. Using this methodology, setting the control gain is very simple and is independent of the system parameters, namely the parameters, namely what? The Kv equal to root of 2 root Kp. 2 root Kp. Okay, 2 root Kp. So what is 2 root Kp? How we obtained 2 root Kp, please? Anyone? This is a second order system, right? You just you compute the Kp value. So what is Kp, Kv? So S square x of s plus Kv times s x of s plus okay, Kp times this. So s square x of s, right? S square plus Kv s plus Kp equal to 0. So for getting a unity damping, so what is Kp and Kv? You compare with the second order system, 2 zeta omega n s plus omega n square. What is omega n square? Kp. So what is omega n root Kp, right? So similarly, what is 2 zeta omega n from this comparison? From this comparison, 2 zeta omega n is Kv. So what is zeta? Zeta equal to Kv by 2 omega n. Omega n. What is omega n? Root Kp. Okay. So zeta equal to Kv by 2 root Kp. Understand or not? Root Kp. So being the critically damped, we are generating the control of our critically damped system. So zeta equal to 1. So when zeta equal to 1, what is Kv? We will be getting the relation Kv equal to root, okay? Kv equal to root Kp. Okay, this must hold for critically damped. Okay, this diagram, the partition control used to control the system in the previous diagram, right? Understand or not? So this is this from this equation, this system, the control gain, gains are totally independent of system parameters. Understand? So let us see one example. If if m equal to 1, b equal to 1 and k equal to 1, determine alpha, beta and the closed loop controller gains Kp and Kv. Okay, so find the solution for this. What will be the solution? Okay, Kp and Kv for position control system, okay, position regulation for position regulation control law, which results in critically damped control law for zeta equal to 1 and k closed loop k dash, okay, k dash equal to 16. Previous similar to the previous problem. So what is the solution? What is given here? Okay, we have to find alpha, beta and Kp and Kv. So what is Kp, what is Kv? So stiffness K dash is given. Okay, K dash is given. See, K dash is given. K is given. K plus Kp equal to K dash. Right? So what is Kp? What is Kp? 1. This 16. Kp is 15. Right? Kp is K dash is right. K dash is 16. K is 1. 16 minus 1, 15. Right? Okay. Let us choose if alpha equal to what is alpha? What is alpha? Can you tell me? What is m? M is 1. So alpha is 1. So what is beta? X dash plus x, right? This is beta equal to x dash x. So what is, so actually beta equal to f dash alpha plus x. So alpha is 1. So simply f dash. What is f dash? X dot, right? F dash is x dot. So x dot. So beta equal to, so that the system appears for the unit mass function f dash as its input. So we then set gain Kp to the desired closed loop stiffness. What is the desired closed loop stiffness? K dash equal to 16, right? K dash equal to 16. Okay. So as it is 16, so Kp is 15. No. Sorry. What they are giving here is in this system, Kp is given, right? Kp is only 16. Okay, not we are not following the previous control gain. So we are going to follow this. So Kp equal to 16. So Kv equal to what? Kv equal to 2 root Kp. As we found here, so Kv is root 2 times Kp. So Kv equal to 2 times root 16. So 4, 8. So Kv is 8. Understand or not? So this is about the partitioning, control of partitioning, designing of gains. Okay. Next is the trajectory following control. Okay. Trajectory following control system. Okay. Trajectory following control. Trajectory following control. Rather than just maintaining the system the desired location, okay, the desired location, let us enhance our controller so that the block can be made to follow a particular trajectory. Okay, so previous case we fix some desired position, we have to regulate about the position, but here we are not going for desired position location. Okay, our controller will enhance so that the system will follow a trajectory, particular trajectory. Okay, the trajectory is given by the function of time. So the trajectory, say previous method only we fix the position. Okay, x double dot x dot, like that. Here we fix some trajectory. Say trajectory with respect to time. Say for example, x desired position of particular time. At any point of time, we can easily control the robo. Okay, robo position. That is called xd, desired trajectory. Okay, xd is a desired position. Okay, which is desired position with respect to time. This is desired position, okay, with respect to time, right? So we assume that the trajectory is smooth, not like higher order trajectories, only two derivatives. Because if you go for the cubic polynomial or fourth order polynomial, then the controlling is very difficult. Okay, actually in the control system, we should, you see, wherever you go, maximum parameter of your controller is only 3. For example, so PID controller, okay, so PID controller only 3 constants, okay, KP, KD, KI, okay, only 3 controller gains. Why, if say, why don't we have 4 controller gains? Because tuning is very difficult. Okay, so tuning of, if we go for higher polynomials, what is tuning? Determination of the KP, KD, KI. If it is 3, maximum 3, it is easy. If 2, very, very easy. If you go higher than 3 controller gains, then very difficult. So the desired position with respect to time, only this trajectory should be smooth. The first condition is trajectory should be considered smooth. Should be smooth. Clear? So for example, only first 2 derivatives. Here we have first 2 derivatives. Derivatives exist. Then only it is smooth. Derivatives exist. Clear? And that our trajectory generator provides, and the say it is a trajectory generator. Okay, trajectory generator. So the trajectory generator generates only two values, only 2. Okay, that should provide, if x is the normal, then x is the normal position. So xd dot xd double dot. So only 2 derivatives should exist for smooth trajectory. Understand or not? So only at any point of the time, the trajectory at any point of time, the trajectory generator generates these 3 parameters: x, xd, x double dash at all times, right? So we define servo error. So we are going to define. We are going to define a servo error. Okay, servo error. What is servo error? So error between x, d and x. Okay, say for servo error for E, what is E? X desired minus x d. Xd minus x. What is derivative of error? Xd xd dot minus x dot. Okay. Similarly, for second order error derivative, what is that? Xd double dot. This is the desired minus x double dot. Understand? So the error is the difference between the desired trajectory and the current trajectory So the servo error between the desired and the actual position, actual trajectory is E equal to x desired minus x actual. Okay. A servo control law which will cause the trajectory is as following. So again we are going for control law as following. What is the trajectory following? F dash equal to xd double dot, right? See, you see the difference between this and the previous case. Xv E dot, okay, plus Kp E. So this is the trajectory following control law. So for the previous control law partitioning, that is position control algorithm, what is F dash? So we fix the control laws alpha, F dash is alpha times, in the previous system, F is equal to alpha times F dash plus beta, right? So this alpha times F dash is F dash as only, what is F dash? In the previous case, the alpha equal to M, F dash equal to X dot, right? X dash equal to X dot. Here we are generating a new control law. This will cause the trajectory following. So this will cause the trajectory following. Understand? So it is from this equation, the control law is a good choice. It's a good choice if you combine it with the equation of motion. If we combine with this with the equation of motion. What is the equation of motion? X double dot equal to xd double dot, okay, for the unit mass, okay, xd double dot plus kve dot plus kpe. So x double dot equal to this. Understand or not? Because same thing, f dash, sorry, here I forget this. So f dash equal to x double dot for unit mass system. Okay. So either this or now, or this is this equation caused the trajectory following f dash equal to x double dot. So what is here? So I bring this x double dot to this side. So this equation becomes what? Xd double dot minus of x double dot plus kv times e dot plus kp times e equal to 0. Now tell me, what is xt double dot minus x double dot? You see, xd double dot equal minus x dot. This is the error trajectory. That is e double dot. So e double dot, double derivative of the error plus kp times e single dot, sorry, kv times sorry, kp times e equal to 0. Understand? So this is the new control law for trajectory following. So this control law develops for trajectory following. Now tell, what is trajectory following? How to, for this we can generate the control system. So the control system following this controller trajectory. So this trajectory we can develop the control system. Okay, control system mainly the computer, the controller, unit mass m, just we are improving the control system block diagram. Robo system, clear? This is the improved version from the previous one, right? You see, what are the modifications we are doing? How we are slowly moving to the complications. Finally, the forthcoming class, we will be doing advanced controllers by enhancing the linear controllers. That's why I am slightly moving from linear. Then only you can able to understand. Okay. What is the input the robo system? F. What is here? F dash. So unit mass. Clear? So this is xd double dot, xd double dot. Okay, what is xd double dot? Xd double dot equal to, this is plus, this is what? This is e dot. Say first we see this, then only you can able to understand. So this is x dot, xt dot, this is x dot. Okay, x dot. This is minus. Okay, this is also minus, plus and minus. Plus and minus. Clear? This plus, this also plus. Clear? So what is this? B times x dot plus k times x. So this is x dot, sorry, x, this is x dot. So this is position, actual position. This is actual position. This is actual velocity. Actual velocity. Understand? So what is e dot? This actual velocity. This is actual position. So xd dot minus x dot is e dot. So similarly, x dot minus x equal to e. Okay, error. Sorry. Sorry. So desired position minus actual position is e. So e into kp, e dash into kv. So x double dot equal to f dash m this. So this control system implies with this relation. Okay. So this is implemented. This control law implemented in the control system block, in the next diagram. So this is implemented in this control system. So plus, this is plus f. Okay, so this is the trajectory following controller for the system. Okay, this is the trajectory following controller for robo arm or robo system, right? So since this is second order differential equation for which we can choose the coefficients, we can design any response we wish. Often critical damping is our choice. Critical damping is our choice. Okay, such an equation is sometimes called, be written as error space. Okay, so this choice, the controller choice, is written as error space, since it describes the evolution of error related to the desired trajectory. Okay, so this diagram shows, the figure shows the block diagram of the trajectory following controller. So if our model is perfect, our knowledge of m, n, so if our model is perfect, if our model is perfect, okay, perfect, then the choice of our knowledge on our choice of m, b, k. Okay, this is based on the linear model, right? Our model, linear model. If there is any noise, okay, this is sorry. If model is perfect, our choice of MBK if there is no noise, no initial error, then it is working, right? So then if there is a noise or error, okay, there is a noise or error, the block will follow the, okay, understand. First, let me clearly tell you. If model is perfect, our choice of MBK is MBK, and if there is no noise or disturbance force, or and no initial error, okay, no initial error, then our control system shown will follow the desired trajectory exactly. Understand? Now you can easily understand. If there is error, text condition. If there is an error, that is either this error due to initial error or noise or disturbance, right? So this will suppress, this will be suppressed, okay, suppressed according to the law, okay, according to the law, okay. That is this will suppress according to this will be suppressed according to E double dot plus KV times E dot plus KP times E equal to 0. Because there is error. Okay, if error exists, so this according to the system. Okay, and thereafter it will be suppressed according to this, and thereafter, okay, the system will follow the trajectory, okay, trajectory exactly, okay. If there is an initial error, even for disturbances or noise, you don't consider. If there is an, okay, if there is an initial error, so initial error means suppose if we set x desired is 10 centimeter, x actually is 9 centimeter. So the robo initially at 9 centimeter. We set a desire initially when the controller starts to control the position. So initially there is an error. Okay. So what is the error? 10 minus 9. So 1 centimeter is error. So if there is an initial error, the system will be suppressed according to the law. So this will be suppressed according to this law, and thereafter the system will follow the trajectory exactly, right? So with this we finish the position control partitioning system and the trajectory following controllers. So hereafter we will be continuing on our journey, our control of robot journey continues on the trajectory following controller. Okay. Thank you very much for your kind cooperation and patience. Thank you very much.
Thank you, sir.